Hi everyone. It's my pleasure today to welcome Aleksandra Ćiprijanović from Fermilab, and Aleksandra's research focuses on the application of artificial intelligence and machine learning to astrophysics and also to high energy physics. And today we're going to be hearing from her on bridging the gap between simulations and survey data using deep learning. So if you have questions, during the talk, please send them in a private chat. So slowly take it away, Aleksandra.
Thank you so much. Thank you for this great introduction, and thank you so much for inviting me. I'm super happy to be here. As you've heard, I'm going to tell you a little bit about using machine learning and deep learning in astronomy, and a problem that probably most of us that want to use deep learning in astronomy will have or already had. So this is a problem of how to use deep learning when you have multiple data sets that you want to work on, and you want your model to work on both. So I'm from Fermilab. I work in the scientific computing division, and I put this image here on purpose. So this is an example of two-domain situation. So this is the main building of Fermilab called the Wilson Hall. And obviously you have one detector image, so the photograph, and you have a simulated, very roughly simulated image or a drawing of the same building. And when you want to use deep learning to recognize this image, for example, unfortunately, these tiny differences, or in this case, not that tiny, will not allow your model to work with both data sets. And in astronomy, we very often have a case where we want to be able to do that. So how to do that? That's basically the talk, the topic of my talk. And I'm sorry, I do not know what happened. 1 second, let's go back. This always happens somehow. Let's go back to the slideshow. Okay, so we're back. So this is basically my talk outline. So I will try to introduce a little bit more where do these data set discrepancies come from in astronomy. I will give you an astro example of the topic that I work on, but feel free to extrapolate this to absolutely any other problem, astro or non-astro, where you have a similar situation. I will tell you what domain adaptation is, what are these methods for deep learning, how they work, and hopefully convince you that they are helpful in this kind of problem. Yes, let's see. In astronomy, you often either have two data sets from two different telescopes, for example, or you have a situation where you have simulated data and real data. They will be different, tiny differences, but still they will be different. If you have two telescopes, of course, they're going to have different specs. Hence, the data is going to look a little bit different. If you have simulation and you have real data, first, these will be different because the simulated data will not include all of the details. That can be either because we don't know all of the physics, so we are not including something, or we maybe don't understand it fully, or because just our computational resources are not limitless. So we have to approximate some things so that we can run our complex simulation in our lifetimes. So all of these things, of course, make the data set look slightly different than real data. Then on top of that, we usually add observational effects like adding observational noise or blurring by the PSF so that we can mimic a particular telescope and make a mock data. But again, you will not perfectly mimic the real deal with that kind of observational effects. And these might not even be obvious when you look at them, but for a deep learning algorithm, very often, this is enough to make a problem. So on the left, you have an example of simulated and real data. And this is an example of merging galaxies. On top, you have a couple of examples from illustrative simulation. And when you have a simulated data set, this is usually the data that you know very well. You have labels if you want to, distinguish different types of galaxies, for example, or mergers versus non-mergers or something. You know what's going on in the simulation, so you know what the object is representing in each image. You can train on this data set. I will probably very often call this data set a source data set. And on the bottom, you have your target data set. This can be observation, for example. And in particular, for example, if you have new data, new observations, this data set is very often unlabeled. So you can't directly use it for a supervised learning algorithm. So that's the problem, basically. So, okay, the previous slide was a hint. We're going to be talking about merging galaxies. And I definitely don't have to convince you why merging galaxies are important for astrophysics. They are a crucial part of the evolution of matter in the universe, and then formation of different types of galaxies, changes in star formation rates, chemistry, types of galaxies in the end. So we really need to understand this process very well, because it leads to all kinds of different interesting things that we want to understand. How do we do that? Well, we have to leverage big data sets of merging galaxies, because this is a very long process. It lasts millions of years. So we can't really study a pair of galaxies merging. We just have to find a lot of them in different stages of the merger. The problem with that is that with observations, to be sure that something is a merger is not really easy, especially if you want to do it on large scales. Very often, if you want to make a big data set of merging galaxies from observations, you have to visually inspect them. That's prone to all kinds of biases and errors from the people who are looking at the galaxies. And sometimes they can, for example, just visually overlap. You need further observations, for example, spectroscopy, to make sure that they really are near each other and not just visually overlapping. All those things make all sorts of problems. So basically the solution is for us to find a way to combine observed and simulated data so that we can learn from both sources and also learn from the similarities and differences between these data sets. When we look through like the history of how mergers were recognized, first we had standard classification methods where you have your image, you extract, you kind of summarize the data and the shape of the galaxy by calculating some kind of parameter, like how concentrated it is, how asymmetric or clumpy the galaxy looks like. And then you decide on some rules based on these morphology parameters, shape parameters. And well, you just classify whether something is a merger or a non-merger based on those things. So the next step, and a very logical one, was to use a simple machine learning model. So for example, in 2019, random forests were used to do the same classification on the same shape parameters, but you don't decide on any of the rules now. So you don't decide how clumpy or how asymmetric a galaxy has to be. You just give it all the parameters to the random forest, and the random forest decides how to classify these two classes, basically mergers versus non-mergers. And it was shown that actually this outperforms all of the separate methods that were used before. And when you think about it, you're still kind of doing this classification on some kind of summary, which is definitely not a perfect summary of the complex shape of the galaxy. So a natural next step, which was done in one of my old papers from last year, is to just not summarize the data. Why would we do that now that we have the computing power, to work with full data? So we decided to use deep learning, use convolutional neural networks to use the full image and all of the information contained inside to classify things into mergers and non-mergers. And for that, we used a very simple neural network. So it had 3 convolutional layers and 3 dense layers. And what we've seen there is that we actually outperformed all of the methods before. So it was very promising. And this is actually how our data looked like. So we were using illustrative simulation that you saw on the previous slide. And we were using distant merging galaxies, so redshift 2, because we wanted to do a tougher task, not nearby galaxies, but also just because this area of around redshift 2 is very important for like large star formation rates, and probably mergers were very important in this period. So let's see if we can do that. We created 2 levels of like observational realism when we were making mocks. First, we just added the point spread function of Hubble telescope. So we just blurred a little bit. And then the second data set, we also added the observational noise. And now we're still just working with the 2 data sets separately. I'm not trying to combine them. We saw that we can get accuracies almost up to 80%, which for this data set is really good. It's not puppies, unfortunately, so it's a little bit harder. And yes, so we could do it, but that is when I try to use the model trained on the top row and classify the bottom row, and vice versa. Oh, and by the way, this is how the galaxies actually look like. So this is the same thing as the top row, but logarithmic color map. So you see that there's a lot of stuff in there, just very faint. Okay, so what happens if we try to classify the other data set? Well, this is what happens. Accuracies were 50%. And keep in mind that these 2 data sets are exactly the same. The galaxies are exactly the same, and we just add the noise. So it's not even different looking galaxies, which would happen if one of these was actual, observed data. So how can we combine different data sets? This is when I really started thinking about domain adaptation. So what happens when you train a neural network for this such a simple like 2-class classification task? The neural network translates your images into a latent space, which, the internal, it can be, very multidimensional space of the neural network. It tries to distinguish between 2 groups of objects and finds a decision boundary between them. When you load a new data set into a model trained that way, it unfortunately is translated into the latent space on some, like it is either rotated a little bit, moved aside or something like that. It just doesn't align perfectly with the old data because the data set just looks a little bit different. So the decision boundary from before doesn't work on the new data set. Well, domain adaptation is added during training, and it allows the new data set to align on top of the other one, and so that you can find a common decision boundary. So this is in essence what domain adaptation does. So on the technical sides of how the training works, so let's first see how you train regular supervised learning algorithm. You have your images, they have labels, in this case, mergers and non-mergers. The network trains, finds useful features, and actually I'm plotting real useful features for this data set in the middle, this blue thing. This is called a grad cam. It shows you which pixels were the most important for classification into a particular class. And for mergers, we found that peripheries of the galaxies are the most important. It does make sense. You have a lot of faint, asymmetric, interesting features over there that you need to look at to recognize a merger. Okay, so but when you train that way and you show it in the testing phase, a noisy version of it, it will not work on the noisy. With domain adaptation, the training uses labeled source data and, very importantly, unlabeled target data. It just uses it to find somehow domain-invariant features. So it moves from things that are useful only for one domain to things that are useful and common in both domains. So that in the testing phase, it can work on both data sets. And this is actually what really happened. I'll show you one more example later on. The important regions moved from the peripheries to the centers, because obviously the noise destroys the faint information. So the useful things for the noisy data set only remains in the center where the signal is brightest. So this is how you technically do it. You have your loss function that the neural network is minimizing from epoch to epoch during training. And these are the 4 losses that we were adding. I don't have time to go through all of them, but I'll focus on the last one, the transfer loss. So first you have your standard task loss. That's the loss that is doing the classification part. It's learning how to classify things. Then you have transfer loss that's adding domain adaptation. And then you have these 2 middle losses, Fisher loss and entropy minimization. These are helper losses. You don't have to add them. They are, both of them do the same thing, but one works Fisher loss in the source domain and entropy in the target domain. Both of them are trying to make the classes in the latent space as compact as possible and as separate as possible, so that when you find the decision boundary, it has a lot of clean space in between, and a fewer number of examples are going to be found on the wrong side, basically. So sometimes it can help to have these 2 things. So when it comes to transfer loss or domain adaptation, you have 2 different approaches and 2 different groups of methods. These are methods that are very, very often used for self-driving cars, for example, because you have to have a car that is trained on images of streets from one town, but it has to know how to drive in all other towns too. So this is kind of tough. So the 2 approaches are on the left, you have distance-based methods. And for that, we used an example of using maximum mean discrepancy. I'll tell you a little bit more what it is on the next slide. It's a way to calculate the distance between 2 probability distributions. And the other methods are adversarially based. So you have a method that trains in some kind of adversarial way. I'll again show you what we used. We used domain adversarial neural networks. So this is the most important part. And yeah, on top, we use a very standard classification loss, which is the cross entropy loss, where Y are labeled, Y cap are predicted labels, and we're just minimizing this loss, penalizing all of the wrong classification. Okay, so let's start with MMD. So this is a super simplified way of explaining what's going on. So let's see, how can we see how similar P and Q, these 2 probability distributions, how similar are they? We don't know them. We can only observe some data points, blue and red, from these 2 distributions. So what MMD does, it transfers the whole problem into the space of kernels, into reproducing kernel Hilbert space. So you substitute each data point with a kernel, and so that we can keep it super simplified on this slide, let's say that this is a Gaussian kernel, but you can use any kind of kernel, and even sums of kernels, even infinite sums of kernels are still kernels. So you can use whatever you want. You sum up all of the blue kernels, all of the red kernels, and you get these 2 curves in the bottom right. So if you, you can also describe the whole curve by just its mean embedding, which is just the sum of all kernels and divided by the number of kernels. This is just how things work in this space. And if you say one mean minus the other, you get this black curve, or the witness function. Obviously, the witness function will be 0 if the 2 curves are exactly the same. So what we want is to add this as our transfer loss, try to minimize it, try to force the network to somehow find the features that will lead to these 2 distributions looking as similar as possible to the neural network. Technically, this is how the equation looks like. So you have 3 sums of kernels that are self-similarity kernels for the blue and red, and 1 with a minus sign in front with cross similarities. So in case, super simple case of dogs and fish, you will have a matrix like this with all of the examples. On the diagonal, you have self-similarities. These are going to be large. And then off-diagonal elements are cross-similarities. We're going to force the cross-similarities to become as big as we can, so that this 3rd term is biggest, and hence MMD distance is the smallest. So basically, we're forcing the network to see dog and fish, something like this, or in our case, mergers and non-mergers. So that's one method. The other method is DANS, or Domain Adversarial Neural Networks. So with these, you have the network that's slightly different than the regular one. You have the convolutional layer, the feature extract, the green part. You have the blue part that's doing the classification. So it's looking at labels. And then you add this second pink branch or domain classifier. It doesn't care what is, 1 second. This always happens. Okay, so it doesn't care about the labels. It doesn't care if something is a merger or non-merger. It just knows the domain labels. And the most important part here is the gradient reversal part for this branch. So the loss in this part is actually increasing. So what happens during training, we are forcing the green part to extract features that are going to be very useful for the blue part, so for the classifier, but very useless for the domain classifier. This means that we are searching for domain-invariant features so that we want to fool the pink branch. And basically you can see that the approach is different, but the result is the same, like with MMD. So here is how things actually look. So you have the two data sets here. The two colors are the two classes. Before training, they're completely separate. This is, by the way, a t-SNE plot, which shows like a 2D representation of the multidimensional latent space. So the source domain are these see-through images. If you train a regular classifier on the source domain, you get something like this. Now the source domain is on the bottom. You see that the blue and red are now separate. The accuracy is quite large, over 80%, but the target domain is completely separate and mixed. It doesn't work on the target domain. If you now, instead of doing this, train with domain adaptation, let's move that aside, you get something like this. So the two domains overlap completely, and you can see the target accuracy increased almost to 80%. So roughly 20% increase in accuracy, which is great. And if we look at where the neural network is looking, so something like in some of the starting slides before, for the merger class, you see in the source domain, if there's no domain adaptation, it looks at the periphery. But in the target domain, it focuses on the noise. And obviously, it doesn't work. But if you add domain adaptation, it starts for both domains looking at the center. And I'm also going to show you what happens if you also add Fisher and entropy loss. This happens. So it's still looking at the center, but also the classes are a lot more separated than before. This isn't necessary, but sometimes it is useful. And finally, can we actually use this for a real problem? So what happens when we don't have a simple difference between data sets like now with just the inclusion of noise, but we actually have simulated data and real data. So this is the problem that we try to do. So we wanted to work with real data. And for that, on the bottom, you have examples of SDSS, Galaxies. And we use that because we have Galaxy zoo labels, so we can test if something is okay or not. And since these are nearby galaxies, we also use the illustrators, but now not distant galaxies. We use nearby, like final snapshots. So this means that in both data sets, unfortunately, we have a very small number of individual objects. We do augment this data, but still the whole data set is like 3 times smaller than the previous example, which is not ideal. Plus, you can also see that the difference, for example, if you look at the left row, is quite substantial. So mergers in SDSS are often like mostly containing the easiest examples because human labelers were the most certain about giving this a positive label of a merger. On the other hand, in simulation, you can have whatever the simulation produces. On the right, you can see the results. So this is a rock plot. If you don't know it, what this means is you just look at the area under the curve. The bigger the area, the better the classifier. So the classifier that is perfect, it has the curve is moving towards the top left corner. If it's random guessing, it's close to this diagonal line. In these 3 solid lines are showing us the performance in the target domain, the one that has a problem. So you can see that the blue and violet curve are not very good. They're kind of very close to the diagonal. So this is training without domain adaptation and with domain adaptation. So we were very unhappy about this, but we thought, okay, we have two problems. Data sets are very discrepant and very small. Let's try to solve at least the very small part of the problem. So let's use the model trained in the previous example on distant merging galaxies, because merging galaxies are still merging galaxies. There must be something useful. So let's start from that model, and then not from randomly initialized weights, and we basically did transfer learning from that, train a little bit more with domain adaptation on the new data, and see if we can make it work. And we did. Accuracy increased again by 20%, so the yellow curve. So even in this very tough and not very good example, we were able to do it. So if you have bigger data, this is going to be even easier. So finally, I guess I want to say that I hope that I convinced you that domain adaptation is something that we should care about. It's something that is going to be crucial for real life applications of deep learning for astronomy. It's going to allow us to work with new observations, especially if, for example, LSST, when it starts running, if we do this correctly, we are going to have a model that is going to be able to do something even in real time. For example, if you want to search for interesting transients during the observations as soon as they start, for example. Without domain adaptation, probably the performance is going to be a lot worse, or it's not going to work at all if we just start on the simulations that we have now. Domain adaptation can really increase the robustness to all other kinds of problems, just like telescope noise or pixel level problems. I don't have time to go into that. That's something that I'm currently working on. If you want, we can talk a little bit about it afterwards. I have an example on the next slide. What I noticed is the domain adaptation really just overall helps the model, increases the robustness, and forces the model to focus on real things and not on noise or some other kind of problem like that. One thing that we have to keep in mind is that this is not very easy to do. So the smaller the gap between the data sets, the better. So we need to, when we're making mocks, we need to try to make them as close as possible to the real data set. Also, if the two data sets are very weird and different, doing domain adaptation with methods that align entire distributions is sometimes not enough. So these that I showed you are doing that, but there are more sophisticated methods that align class on top of class. So in cases where you have weird looking and different looking data sets, and maybe in one you have additional class that you don't have in the other, methods that do class by class thing are going to be better. So yeah, and finally, of course, I want to thank all of the people that work with me on this and that still are working. You can see just part of them here and a part of institutions that are involved in all of this. So, if you want to talk about any of these things or connect to any of these people, please let me know. So thank you so much. And yeah, if you're interested in AI for astronomy, check out the Deep Skies. It's an amazing community with a lot of astro people and a lot of non-astro people, and even from industry, all like interested in AI for astronomy. I learned a lot from them, and also it's very good for networking. So yeah, feel free to ask me about that too if you're interested. Thank you.
Hi, Slady. Yeah, like, so, thank you, very much, Aleksandra, for a really like cool talk. Just a reminder to everyone to send your questions in the chat to me. And to begin with, we have a question from Morgan about visualizing key data features.
Thank you. Yeah, so thanks so much for this. And I'm thinking a little bit about sort of back to where you started, which was, say we have a simulated data set and the real cosmos, and we want to compare them. And you made this point about the simulated data set never having the kind of like full physics. And so I was wondering if you could talk more about that aspect of it, in particular with kind of the idea that what can we learn? How do we use that to basically learn how to constrain the physics in the simulation? So say we are doing this comparison with the purpose of learning something about the sort of simulated physics. How does the sort of adaptation between the simulation domain and the real domain inform what we do? And is, like, you showed us these kind of amazing visualizations of the key features. Is that part of that sort of story of how, we learn? Like in terms of, say, I was somebody who was trying to improve a simulation based on that comparison. How would that work?
I love where you're going with this. So I think that we can actually use something like this to try to learn a little bit about our simulations. So whether we want to learn about the simulation and the physics, or whether we want to learn about which things are important to add on top of the simulation to have things become closer and closer to real data, I feel that in both cases, we can use domain adaptation. And this is how I kind of see it. So I would, in this case, make a test where you include, if you are lucky not to have a super big simulation, but something that you can actually work with, you simulate something that is kind of a crude estimate of the real data. You train the model, look how distant they are, look where the model focuses, and then just start adding more and more things on top of it, resimulate, but do a better simulation basically. And basically observe, will this lead the new model to see these two data sets as something closer and closer together? Maybe you don't even have to train a new one. You train something on a simple simulation. You show it the real data. It's going to be somewhere very far away. Then you also show it some other simulations that are somewhere in between. And look if they're going to be, closer and closer to your data. And maybe by looking at these distances, you can kind of see which things are more important, which are less important. And the same thing you can do for adding observational realism. So look how much the noise level in fact affects the data. Will it move a lot or a little bit? And which things, or even when you look which things were the most important for classification, like those rings that I showed.
Yeah.
If you add noise, for example, you can look which level of noise will make the model stop being able to see this as an important feature, for example, and move to something else. Something like this. Of course, this is not, you have to always do this with a grain of salt, because you can't, when you're doing things in a lot of dimensions, things are not easy. So I think that we can develop even maybe better metrics or just be creative and think how to use the information we can extract from the data. It's kind of not something that is standard now. People just, try to understand and improvise. But I feel like there is something there. We can try to understand stuff from tests like these. And these are things that I really, currently I'm thinking about. So hopefully I'll, in the near future, maybe even we'll have things to show you, some examples. Cool. Yeah.
Yeah. So, I mean, I heard a couple of amazing things, but one is like maybe that this distance measure can become a metric in and of itself.
Yeah.
And the other is that, if you're thinking about like, even if you're designing an observational strategy and you want to use certain features, you could ask like what noise level obscures the network's ability to recognize those, which I think is kind of amazing from a planning strategy. That's super interesting. Well, thank you so much.
Okay, cool. So now we have a question from Avi about how to find unexpected objects. So Avi?
Thank you, Sarah. So my question is based on experience that I had when I was a postdoc many decades ago. I remember seeing back then the Astrophysical Journal was in actual volumes in the library, not online. And I remember seeing, that was in the 80s, images in the Astrophysical Journal of giant arcs around galaxy clusters. And until the mid-1980s, nobody spoke about gravitational lensing as a possible explanation for those. And people just ignored these. They were published in the Astrophysical Journal. You could see these arcs, but nobody paid attention to them. And my question is, perhaps deep learning will do a better job than scientists in the sense of finding things that the simulations do not expect, that scientists are not expecting, but we would see things that otherwise we would ignore. So the question is how to put that into the software.
Mm-hmm. So a lot of people currently, some people currently doing deep learning for Astro are kind of asking the same question. And I've seen a couple of different approaches, but I think that the main approach where people are trying to use a slightly different method. So not a supervised learning method like here, not train on a specific task and have examples with labels, but just have only images and try to leave the model to train on images and try to somehow see what's similar and what's different and somehow translate that into its latent space. And you can look inside of the network and see where things are located in this space. And if you have something that is very weird and doesn't look like some things that are common, it's going to be somewhere far away. And I remember recently looking at a paper that did this for galaxy morphology. They wanted to see if the network is going to, on its own, see that there are like, for example, 3 groups of objects like spars, ellipticals, and irregulars and mergers, or is it going to decide that maybe something else is there and that the network can clump together as a separate class. And yeah, well, it turned out it does have the same classes. They didn't discover anything super interesting and new, but those sort of methods will also show you weird things, and they will be either very far away or somewhere on the edges of the whole distribution. So those things are useful. I mean, something like this you can also, of course, use, but if you're training it on one task, everything that's not that task is going to be strange. So it's a little bit harder to see if something is really strange or just not included in your training data set. So yeah, I think it's definitely going to be useful because finding weird things with a terabyte per day with LSST is not going to be feasible for a human, I think. And even for lenses, I know that for DES, I think that people found with domain adaptation, maybe like 100 and 200 new lenses just by using that after humans went through the entire data set and found everything that they could. So yeah, I'm hoping that this will be very helpful. And who knows, maybe people devise other ways of finding weird things too.
Yeah, like I just like to follow up on like that. You said that the neural net slowly was able to find slowly more objects than humans are able to identify. Like, because there also were qualitative difference between the types of objects is identified, and like the objects, yeah, like slowly, like that slowly, like that humans are able slowly to see.
Very well, yes and no. Depends on the situation. So I don't remember the exact paper for the lenses, the example that I gave you. If you use a supervised learning method and you give it some example of lenses, it's usually going to mostly find similar things because that's what it was trained on. But it doesn't have to be only that. So for example, with one of the projects that I'm involved in is using these type of methods, so like regular convolutional neural networks, and also object detection algorithms. So algorithms that tell you where the object is, not only, oh, we have a galaxy, but also galaxies right here. These are the pixels of the galaxy. So we are applying these two methods to find low surface brightness galaxies in DES, for example. And the current biggest like DES catalog, I know people who had to look through images. They looked thousands and thousands of images and created this very painful catalog. But after we started using deep learning, first of all, we of course found all of the things that a human could, but we could also find things that have an even lower brightness. So it still depends on how you pre-process the images. So, I mean, it's not like super fully automated, but the pre-processing is basically the same, like was done before, but we could find fainter objects. So I think that it can help us go further, maybe not in this way find completely different looking things, but things that are similar to what it knows, it will be able to find better than we can. But yeah, maybe some other methods like the one that don't require labels will help us, like I mentioned before, find different looking things. Or at least say, tell to us, well, this group of objects is something that I see as something similar, and you inspect it and you see that that's something new, maybe something like that.
Oh, okay, cool. Yes, like I also have quite a general question. Like on slide 10, you were talking yes, I think slide 9 or 10, like you were talking about hiding the data according to decision boundaries, and you've drawn them as lines here. Are they usually assumed to like be flat surfaces in your slowly your parameter space, or how do you control their shapes?
Yeah, that's a very good question. So they are never simple looking or flat or anything that we like, but they will be whatever, depending on the problem. So the plots that I was showing, those are called t-SNE plots, and they're not very ideal way of plotting the multidimensional Latin space, because they do translate it into a 2D. They're just looking at the similarities between the two distributions, one in 2D, one in whatever ND that you have. But they're not keeping the distances between data points very realistic. So that, like, for example, if you have a region that has more dense population, you'll just have that as a big blob on a t-SNE plot. It's kind of weird. And t-SNE plots also they have some hyperparameters that you can fine tune. So the data will look a little bit different. So yeah, you need to use them just for kind of understanding what's going on, not thinking about them very precisely. There are better methods. Again, nothing is ideal, because how can you really fathom the distribution in n dimensions? Everything is super close. The boundary is always near. It's very weird. Things are very always near the edges. But for example, here, it's a different example. I can tell you what it is. Here, it looks kind of similar, you see, but this is a UMAP. ISOMAP. In ISOMAPs, you do a similar thing, but better. You calculate geodesic distances in the n dimensions. You, I don't know, decide how many examples you want to track, and you see how distant they are in the space. And then you translate to 2D, trying to keep the geodesic distances the same. So these distances that you calculate somehow here. So in ISOMAPs, the actual positions of the data points is a little bit better. It describes the space, the original space, a little bit better. So yeah, this is a newer plot, so I moved away from t-SNEs. I don't like them. They're not very good for quantitative things. Yeah, so by the way, this example is slightly different. It's still domain adaptation, but I'm trying to do galaxy morphology. And I'm actually studying what happens if you perturb one pixel of the image. So like looking at if like a CCD readout has a problem, you have a cosmic ray, whatever, something. Also like compression and decompression of images. Our data is going to be very high resolution. We're going to compress it, decompress it. And unfortunately, this sometimes leads to tiny errors. It's just the way things are. And I'm doing 1 pixel attacks as a proxy for a possible problem like this. And looking if this makes the network that knows what spiral, elliptical, and merger are. Can this make the classifier wrong? And yes, it can, of course, unfortunately. But doing domain adaptation, so helping it understand, so for example, different noise levels also increases robustness to these kind of problems. So you basically have 2 gains with just like doing one thing. So yeah, this is something newer that I started testing. But yeah.
Oh, cool. Yeah, that's super interesting. I think we have time for one last question from Morgan here.
Thank you. Yeah, so I mean, I have so many questions, but I was hoping you could talk, I guess, a tiny bit more about this last point of, you know, there are certain physical things that we know, or observational or physical, whatever aspects that we know we need to adapt across. And those might be things like, and I mean, you can tell me if I'm interpreting this wrong, but it sounds kind of like never trust just one pixel to make your classification almost. And so I'm wondering if you can talk more about that point that you made about like improving, like training the domain adaptation on like one kind of noise or something, improving the performance with respect to, say, cosmic rays or something like that. So like what is it about the domain adaptation that like encodes that transferability? Or I guess like qualitatively, I understand this idea that it makes the classification more robust, but how does that actually happen? I don't think I understand that.
So the whole point of domain adaptation methods is that it helps the network try to find domain invariant features to use. So if you have a different noise model or noise level in some of the images, that definitely needs to be a feature that you are not going to use, because that's not translatable. Okay. Yeah, so it's forcing it to see that this is different. I cannot find the same thing in two data sets. I'm just going to try to focus on something that I do see. And for that reason, of course, when the noise is the problem, you just start to disregard the noise. Yeah. And because in this case, for example, when the noise is the problem, or like, this is exactly the example that we can use. So here we're making mocks of LSST 1 and 10 years of observations. And we're training on the less noisy, so around 10 years, and we're domain adapting to the 1 year, but you can do vice versa, it doesn't matter. And because it learns not to care about the noise, not caring about the noise also helps it not care about that one pixel that is wrong, for example, if I attack it. So that's also kind of part of noise. So what we've seen here is that not only, of course, the domain adaptation help it classify things in both domains. We knew that that will happen. But what we've seen for like additional problems like those one pixel attacked images, the distance you have to travel from the original image to the one pixel attacked image that is actually successful in fooling, so to cross the decision boundary, is, I think, 2.3 times larger in this example. So you can still theoretically fool the model, of course, because we're attacking it here with an efficient method. But in reality, because the distance to cross the border increased so much, probably most of the actual problematic pixels are not going to be, unlucky enough to be able to cross. So you basically not only get robustness to the thing that you trained on, you get robustness on other kind of similar things, but not the same. So yeah, when you mention distances between stuff, we actually try to calculate this here in this example. So yeah. I have metrics, maybe not that much in the short archive paper here, but soonish there will be a bigger paper with the distances and everything.
Amazing.
Yeah.
Thank you.
Okay, well, we've run out of time, and so we'll end like there. But Aleksandra, if you would like to say some final words to summarize and conclude here.
Sure. Yeah, it was very fun, very great. Thank you so much for inviting me. I hope I try to convince you and explain that with huge data that we already have and what we will have in the future, hopefully next year with SST, we'll see. We are going to have to make models that are better than what we're using now. We're going to have to make models that are going to allow us to work with multiple data sets. And domain adaptation is definitely going to be one way of doing that, because it's going to help us really find common things between data sets. And hopefully in the future, also, I really think it will. Domain adaptation will also help us understand the physics models, as we were talking about today, and also understand the neural network methods, because we can look inside, see what's happening, and use this information to go a step further to build even better models. So I'm hoping that we can do all of that by understanding domain adaptation a little bit better.
Thank you.
Yeah.
And if you have your thing in full screen and don't get to see the chat, a bunch of people are chiming in to say thank you. So thank you so much. We're really grateful. And with that, thank you all for coming and for your questions.
Thank you so much for inviting me.